Hello everyone, and welcome to this latest webinar from Omdia, Division of Informatech. My name is Alan Tatara, Senior Event Manager for the Omdia webinar team, and I want to thank everyone for joining us. Today's webinar is titled 800G Technology. Does double capacity mean twice the performance? Today, our panel will explore real examples of how 800G can cut network costs, support bandwidth demand, and optimize transmission capacity. Our webinar is co-presented by Omdia and our partners Ciena, Fujitsu Network Communications, and Huawei Technologies. Before we get started, let me highlight just some of the features available for you on today's webinar. So the console you're looking at is completely customizable. You can open, close, move, or resize any of the windows that you have open on your screen and arrange the console any way you like. Now, at the bottom of your console, you're going to see a number of application widgets. I do want to call out the resource list widget, and this is where you're going to find additional material about our topic, including the downloadable slide deck from today's session, as well as other valuable information, including a special report authored by analyst Timothy Monks. You'll also see a Twitter widget, which means you can tweet directly from within the console, and today we're using the hashtag 800G. We will also have a live Q&A session, as always, after our presentation, so please submit your questions or comments at any time by using that Q&A box that is on the left side of your screen. Please note that this webinar is being recorded and that the on-demand version will be sent to you within about 24 hours. And if you experience any technical issues, just click on that question mark widget and you will get the answers that you need. So now let me introduce our panel. First leading our discussion is Timothy Monks. Tim is a principal research analyst in the optical networking technology segment at Omdia. Joining Tim is Kent Jordan. Kent is an advisor in the portfolio marketing group at Ciena. We are also joined by Mohammed Sarwar. Mohammed is a distinguished global product planner at Fujitsu Network Communications. And rounding out our panel, we have Dr. Maxim Kushnarov. Maxim is director of the Optical and Quantum Communication Laboratory at Huawei Technologies. So welcome to our panel. We are honored to have you with us today. So now let me turn things over to Tim so we can get started. Tim?
Thank you, Ellen. And hello, everyone, and welcome to our webinar, 800G Technology. Does twice the capacity mean double the performance? With OFC effectively canceled, this will be a good chance to catch up on new trends and new technology for optical networking and coherent transport. Our sponsors, Ciena, Fujitsu, and Huawei, are leading vendors worldwide and will share their valuable and unique perspectives. Today we'll be discussing 600G and 800G coherent transport with a look at how this new technology can be used in practical networks. We will also compare and contrast it with current coherent transport technology. In the first section, I will look at some of the market trends shaping the industry, and then the sponsors will present information on the problems and challenges facing the industry, new options and solutions, effectively new technology, the deployment applications where this can be used, and finally the unique sponsor approaches. I will make a few concluding remarks, and then we'll have a Q&A session. If you do have questions, use the Q&A tab at the bottom of the console to submit them. Okay, so networks are growing exponentially. They have been essentially. This is tracking new transponder, new coherent modem deployments since basically the beginning of the coherent era starting in 2011. But the bandwidth is growing exponentially, and sorry, I was having a little difficulty advancing the animation. But information is the currency of business and life today, and the optical networks transport the vast majority of the information. We're seeing exponential growth for optical transport networks, and this has been around 30% compounding growth rate. We expect it to continue over the next 4 years, effectively doubling the bandwidth every 2.5 years. in the early part of the coherent era, from 2011 to 2015, the cost per bit was reducing at about 30% per year. And this was holding the spend on optical networking about flat. After 2015, 2016 through 19, we've seen those cost per bit reductions become more incremental, and hence the spend on optical networking has gone up. And we expect that trend to continue, but will this new technology help, reverse that trend? That's an open question, and we hope to help answer that today in the webinar. One of the things that a lot of the optical networking companies are looking at is having coherent modems become more application focused. At the beginning of the coherent era, it was really a one-size-fit-all. All applications, we'll see what can fit with what, but it was one solution for all applications. We're seeing now that coherent modems are starting to be developed for specific applications with the goal of reducing the cost per bit. Moving over, why, I'm sure many of you have heard about the Shannon Limit and all that, but why is the Shannon Limit important? Shannon Limit basically puts in a cap or a bound on the amount of information that can be transmitted over a single signal frequency band limited by the noise. So B is the bandwidth, S is the signal, N is the noise in this, and C is the capacity. As you can see, commercial technology has made great strides, and we are now getting very close to the Shannon limit, meaning we can't go over that, so we expect that improvements will become much more incremental, especially improvements in spectral efficiency. So the amplified spectrum, if you will, where the information is transmitted in frequency space in the fiber, is limited by the amplified spectrum. And by coming close to this limit, to the amount of information we can pack in there, it makes the amplified spectrum increase in value, and it also makes the efficient use of this spectrum become an imperative. And we'll look at how 600G and 800G technology helps with this and improves basically the economics of the optical network in light of the Shannon limit. Higher data rates are really needed to cost-effectively scale bandwidth. We have this doubling of the number of the bandwidth every 2.5 years. Omdia has been tracking this through the whole coherent era. We track by data rate and also the number of deployed modems in each year. And this is showing you some history from 2018, 2019, and then forecasts for 2020 through 2023. We're in the process of updating this, and we'll be adding 2024 and further breaking out 400 gig plus into 600 gig and possibly 800 gig. 800 gig will be broken out at some point, but we're looking to do this. But this is showing you effectively the number of transceivers to meet this bandwidth growth in the future. Now, looking at this, if you were to look at that, that's the same chart. Of course, the y-axis has changed. If you looked at the number of transceivers that would be required to meet that same bandwidth growth using only 100 gig technology, it's a huge difference. It's about 2.5 times more transceivers or coherent modems that would be required than scaling with going to higher data rates. Moving to higher data rates is the most cost-effective way to scale bandwidth for a number of reasons. It significantly reduces the number of coherent modems required. So in this example, which may be extreme because it's only 100 gig, and there are 200 gig and some 400 now, but it's a 60% reduction in the number of coherent modems. This is also a huge reduction in the number of ROADM degrees required, and with that goes the network complexity. So it's a very good step in more cost-effectively growing with network bandwidth demand. And new technology making 400 gig more gig plus more capable is needed. You know, one of the big things is, okay, it's one thing to increase the data rate with spectral efficiency, but spectral efficiency is difficult to scale, especially in longer reach applications, long haul, metro and long haul, for example. And you really need to move to higher baud rates. You know, example, if you move 2 times up in spectral efficiency, your reach or your distance goes down by a factor of 4. If you do that with baud rate, the reach only goes down by about 10% with the appropriate adjustments in signal levels and DSP settings. So effectively, higher baud rates are needed to scale the bandwidth in the longer reach applications. And we really need higher performance to maximize network capacity at reach, as I call it. Okay, in this next section, we're going to go through the problems and challenges facing the industry, and I'm going to now turn it over to Mohammed to give Fujitsu's perspective.
Hi, thanks, Tim. Thank you all for joining the webinar today. Let me start with some of the challenges we see network operators are trying to address. There is no doubt that industry is going through extraordinary expansion at this time, but main challenge remains the same. That is how to continue to scale at sustainable rate, both economically and environmentally conscious way. So obviously, cost per bit should continually drop, but it is important to understand that that does not have to come from the reduction of component costs only. It should also be driven more holistically by a low-cost architecture like ZR-based IP over WDM for short-reach applications, to more common and flexible line system that minimizes the need to refresh it with every new generation of transponders. And we also see that operators are also more interested in improved optical performance and power efficiency. I think these are becoming very important criteria, especially due to perceived little functional differentiation in the various offerings coming in the market. On top, operators are also dealing with a number of options and variables to improve cost efficiency. There are a number of things that are thrown on them. Operators' viewpoint on this slide is based on internal survey and feedback we get from our customers. Y-axis shows operators' priority. And based on their direct feedback, we see that their priorities are different for different applications. For example, interop is very important for short-reach applications to reduce the costs, which are driven primarily by the higher volumes. Industry is also collaborating in the area by offering universal methods to operate in multi-vendor environments. Open ROADM, TIP, ZR, and OpenZR are just a few examples. And yet performance differentiation gets more for the buck for longer transmission distances. And operators are also trying to update their architecture to see how pluggable coherent optics will fit into that, either as direct attach or transponder attach, and how that will find application with the certain cost benefit that are promised to them versus traditional transponders that offer higher performance and also higher density. So we also think that optical networks are still not simple enough to operate. Although optical vendors are providing all the flexibility in the world at every layer, for example, at the transponder, ROADM, or even line system perspective, but harnessing that flexibility and stitching and operating an open optical networks efficiently with dynamic capacity that we always been looking for continue to be a challenge. So with a lot of options in works, we hope that 2020 will bring that much needed clarity to all of us. So here I'm trying to show the fundamental shift that is going on in the optical network architecture. Pluggable coherent optics will be driving that shift. This slide shows that transition from various applications perspective. So I've divided into 3 categories. Blue indicates current traditional transponders. Red is the direct use of pluggable coherent optics, and green shows next-gen higher baud rate transponders that we will see in next few years. So for less than 120 kilometer application, from 20% use of 100 gig PAM4 pluggable use today, I think it will transition to 400 gig ZR and ZR plus 70% of the deployment by 2023. 13% use of high-speed 600 gig transponder operating at 400 gig to 600 gig will continue to grow to almost 20%. And the transponders that are coming along, that 200 to 800 gig, will replace previous generations 200 gig transponders for about 20% of the use in this segment. So the next one is the 120 to 600 gig, 600 kilometer segment. Currently, 100 gig, 200 gig, and also 400 gig rates are used in this segment with almost equal distribution. But that will see a transition to over to 1/5 of deployments using direct attach VR plus running at 300 to 400 gig rates. 2/5 of the deployment will be using transponders with pluggable optics, again running at 300 to 400 gig. And the rest will go to 800 gig and higher baud rate transponders that will be operating at higher rates like 400 to 600 gig. And finally, the long haul segment will see much larger adoption of higher baud rate transponders like 800 gig and higher. So from similar distribution and rates as we have in the metro, it would grow to 10% 400 gig ZR operating at 200 gig, and the rest 90% by those next generation high baud rate transponders running at 400 gig rate. So that's a pretty drastic change in the next few years. And with that, I will hand over to Kent for his views.
Okay, thanks. So one of the challenges we wanted to talk about is around selecting the optimal baud. But what is the baud? So the baud is the number of symbols per second, and essentially it determines how much spectrum the signal is going to take up, and by setting to a higher baud, we can get to a higher line rate. But it's a complex engineering operation to be able to select the optimal baud. So there's a number of different customer or network requirements to consider, and there's also several engineering and physics-related variables to consider as well. On the networking side, we've got requirements to increase the throughput. And for a given throughput, we also want to increase the distance that we can go. We also want to be able to increase the speed of the client rates that we can carry in the network. And so all of these requirements are pointing us to a higher baud. But we can't just go to any arbitrary high baud number, though, because there are engineering considerations on the bottom of the diagram, like the speed of the electro-optics, the speed of the digital analog converters, the number of gates that you can fit into the actual DSP, and how much does all of this cost to manufacture. So all of those items are pushing us towards a lower baud to make it easier to do. So there's a push-pull on the physics and the cost versus the requirements for a higher speed. And at Ciena, we think the best answer to this equation based on current technology is 95 gigabaud. Now, of course, there isn't one baud to rule them all. Different solutions are going to point to different baud depending on the constraints that are being used. So while it's not the only number that gets you to 800 gig, 95 gigabaud does get you there, and it's a good multiplier for 100 gig or 400 gig clients, so you can put multiple clients into a single 800 gig signal. And it's got the performance to push more bits longer distances. And that's going to be important when we start talking about how this applies to an actual network. So with that, I'll go ahead and pass it over to Maxim to talk about Huawei's views.
Thanks, Kent. So when we increase the data rate of coherent optical transceivers, system impairments become more dominant. It's not just about the modem anymore. And we need to take care of the system when we design a DSP. For example, if you look at quantization noise. In the old days of 100G DPQPSK, quantization noise was an afterthought and was modeled really simply. But these days, when we push the modulation order, we need to model the exact behavior of D to A converters as precise as possible, not only to measure the impact which this distortion could have, but also to potentially mitigate quantization to a certain extent. Or laser phase noise. Laser phase noise becomes really critical when we try to transmit a high order modulation scheme like 800G with high order QAM over, let's say, a submarine link. Because here we see an effect of accumulation of laser phase noise in combination with chromatic dispersion, and becomes way more critical and requires more attention. It may require a lower line with lasers. Or nonlinear distortions in the fiber. The latest modems feature constellation shaping, which increase peak to average power ratio of the transceivers. It may, in fact, actually not improve the performance, but in some cases decrease the performance. So it needs to be taken care of on a system level when designing a DSP. Or one more example, IQ skew. IQ skew used to be a very simple effect and solved either by design or a calibration in the factory. However, these days, due to the very small durations of the symbols, IQ skew needs to be tracked and adaptively compensated in the field due to aging or temperature changes or wavelength changes of the components. So the same effect requires way more sophistication in order to solve it. So it's no longer sufficient to look at the single wavelength capacity in maybe back-to-back measurement. We need to look at the system level to evaluate the performance of the next generation transceiver. Tim, over to you.
Thanks, Maxim. In this next section, we'll look at the new options and solutions to address some of these problems and challenges our sponsors have outlined. I'll turn it over to Mohammed now to give Fujitsu's view.
Thanks, Tim. So here I will start with some clarifications. So once we are talking about capacity here, it's really the fiber capacity, that how much data can be transmitted at a read through a particular band of the fiber, not to be confused with per carrier or system capacity. Performance is basically the reach. So generally, capacity and reach are inversely proportional. Higher the capacity, lower the reach. So current generations of 600 gig transponders carrying 600 gig at 64 QAM that fit into 75 gigahertz channels have already achieved practically the highest spectral efficiency of C-band with the fiber capacity of 38.4 terabits. So that has already been done. So spectrally, probably we have achieved the limit. Higher capacity using higher modulation is not much practical. So the next thing which we can deal with is the baud rate. So higher baud rate, if run at lower modulation, can offer better performance. But in that case, it's important to understand is that fiber capacity is not improved. The gray curve on the graph shows that current 64 gigabaud DSPs can achieve 3,000 kilometer reach. I picked that as a reference at around 200 to 300 gig rates. But 96 gigabaud rate shown in the orange can achieve 400 gig rate or higher for the same distance. And taking it further, if we continue to increase the baud rate to 120 or to 128 gigabaud, that's an upgrade from current 600 gig technology in blue curve. We'll shoot for almost 600 gig for the same distance. So yes, high baud rate can improve performance in that sense. This is basically due to the better OSNR that comes from using lower modulation order and also lower power density over wider channel that is used. That allows the signal to be transmitted at higher power, thus improving the reach and helping mitigate impact of increased nonlinear effects. So obviously there are some trade-offs that come with higher baud rates. One, wider optical channel width is required. That directly impacts the spectral efficiency as shown in the simple table on this slide. That 800 gig at 96 gigabaud using 112 gigahertz channel will have reduced fiber capacity than 600 gig channel that fits into 75 gigahertz. This also has a direct impact on the line system infrastructure. That should either be flexible enough to handle new rates as they come along, or will need to be refreshed, and very careful channel planning has to happen to avoid any stranded bandwidth, and also to fit into more logical, generally used and standard channel width options. For example, industry has already made significant investment in the 75 gigahertz line system and 64 gigabit technology. So that's, it's already in the network quite a bit. From generational benefit that come with every generation of DSP, every DSP, new DSP reaps from some of the benefit that come from the technological improvement that has happened since the last one. So as, for example, 600 gig did from the previous one, by providing higher spectral efficiency and truly, for the first time, a flexible transponder that can have variable options for reach and capacity by variable data rate, baud rate, effect, constellation shaping, and modulation growth. It was truly a first flexible transponder. Now, and we can also see that some of the power and asset process improvement that has gone in the last few generations that we have worked with. Now, 800 gig and higher baud rates should offer significant improvement in some of the areas, especially for power efficiency perspective, that will be attributed to deeper component and functional integration and improved fabrication process. This generation should also offer more interoperability options, not only at the electrical or optical level, but also from coherent management interface perspective. That makes it easy for adoption. I also want to clarify a couple of things here. That 1.2 transmission can be offered today using current DSPs by multiplexing two 600 gig carriers into single channel. The other one is that two 400 gig carriers as single channel using today's technology compare well with one 800 gig single channel. I think in both these cases, 2 by 400 gig carriers versus one 800 gig single channel, spectral efficiency and performance in both cases are comparable. But 800 or even higher data rate option could offer better power numbers and relatively lower cost because obviously there are fewer components that are being used. So finally, I would like to reiterate that 200 gig to 600 gig DSP technology and system out there today are the most spectrally efficient system and truly flexible. And 800 gig DSP definitely will be an incremental change and should offer further power and cost improvement for target applications. So with that, I will hand it over to Kent to talk about key enablers for the next gen optical technologies.
Okay, thanks. So earlier we heard about some of the technology challenges related to designing new DSP ASICs and high-speed electro-optics to increase the baud and increase line rates up to 800 gig. So two of the technology enablers we can use to help with the design of these high-speed ASICs and the high-speed electro-optics are advancements in CMOS fabrication and photonic integration. So first off, we'll talk about the CMOS. So 7 nanometer FinFET is the CMOS technology of choice for 800 gig because it's mature. And by mature, I mean it's leading edge, but it's not the bleeding edge. So this is the same process that's been used for a couple of years by the mobile industry in our cell phones, and it's been used by PC video board manufacturers for high-end graphics cards for PC gaming, and people are using those same chips for Bitcoin mining. So, it's been in the market for a few years. The gate size is obviously smaller compared to older technologies, and while it allows you to make the ASIC size smaller, we can still support enough functions and performance to achieve 800 gig. With respect to photonic integration, you've got options for silicon photonics and indium phosphide integration. For high-speed electro-optics, we're using both indium phosphide and silicon photonics. In the past, sometimes people have pitted those two technologies against each other for a given application, but ideally, you want the expertise to be able to choose either one and be able to use the appropriate material when and where it makes sense for the application and the requirements that you have to meet a certain level of performance and integration and economics. So silicon photonics leverages a high-yield fab process, so you can get many more dies per wafer. It's easier to manufacture, and you can achieve a very high level of integration, all of which helps to drive down the cost. Indium phosphide is widely used and deployed as well. It's required for getting to those higher speed electro-optics to get a higher level of electrical bandwidth for these high baud signals, and it's ultimately what gets you to these 800 gig line rates. So again, I'll go ahead and pass it back over to Maxim for Huawei's view.
So how do we double the rate? How do we go to 800 gig? Well, DSP, as mentioned before, is at the heart of innovation. And the latest generation of ASICs will see several key improvements over the previous designs. On the one hand, the designs will use advanced modulation schemes. For example, probabilistic shaping is a technique which makes the signal looks more like noise, which, according to information theory, increases channel capacity. At the same time, we need to use more sophisticated, nonlinear, pre-distortion, and post-compensation for the concatenation of various subcomponents, such as the DA converter, the driver, and the modulator, as well as the fiber. So without advanced equalization, this jump in capacity would not be really possible. And one last example is SOP tracking. It sounds like a trivial problem because it has been solved before. However, if we go from simple modulation schemes like QPSK to higher order modulation, using classical algorithms, tracking becomes more complicated, and we potentially need to redesign the way that we track the polarization in the ASIC and to be able to compensate for fast SOP changes which come from lightning strikes on optical ground wire cables. However, just improving the DSP is not sufficient to double the capacity of a modem. At the same time, as we already heard, we need the right baud. And the baud rate needs to be above 90 gigabaud. And it can only come if we improve analog components, the electrical ones, drivers, ADDA, or of course, optical components. On the right side, you see an example of ultra-high-speed silicon modulator, which transmitted 100 gigabaud using 32 QAM. But here I also agree, there's not one technology to rule them all, and you likely need a combination of silicon photonics and indium phosphide to get to the cost optimum design of your 800G modem. However, if I talk about increase of baud rates, some people may say, well, this doesn't really double my spectral efficiency on the fiber, because in the end, what I want, I'd like to double the capacity of my system, not just the capacity of my given modem. So while we increase and improve the modems, at the same time, need to be taking care of the line system. And going from today's 96 channel extended C-band systems to a 6 terahertz window, ultra-wide C-band. Such a window, one can potentially transmit up to 48 terabits of capacity using 800G transmission in 100 gigahertz spacing point to point. If mesh networks are involved, the spacing may have to be increased to account for WSS filtering penalties. And for operators, which really care about capacity of the fiber because they may have to lease fibers, it is imperative to deploy L-band ready systems today. You can populate the C-band, but the system needs to be L-band ready. So in the future, You can crank up the capacity up to 90 terabit point to point using 800G. And thus, Tim, over to you.
Thanks, Maxim. In this next section, we'll look at deployment applications, where this new technology can be used, basically from DCI applications to long haul. Included will be analysis of various brownfield networks and outline the differences of using this new technology versus 100 gig and 400 gig technology, and answering, helping to answer the question, 800 gig, does twice the capacity equal double the performance? I'll now turn it back over to Mohammed for Fujitsu's outlook.
Thanks, Tim, again. Here I'll talk about some of the future deployment models. Now industry is offering a wider set of tools than ever for operators to help in this architecture shift I just talked about in the previous slide. That helps them in transition, and also that is coming from the improvement in the coherent technologies over the last few generations. Operators have multiple options for each segment of their network that they can leverage based on their scale, their needs, and also the velocity of the change in their network. For example, for short distance links, they'll have pluggable ZR and ZR plus coherent options, 600 gig current generation of transponders, as well as 800 gig and higher data rate transponders for their specific requirements. For metro, additional option will be transponders that offer richer feature set and high performance using ZR plus optics. And in the long haul application, 800 gig transponder will be complemented with the existing 200 gig systems. So with that, I'll hand it over to Max.
Thanks. So when we talk about 800G, we hear some concerns like, what is the actual client rate? There is no 800 gigabit Ethernet. What do you transport using 800G? And isn't 800G only for short reach? Well, for once, 800G offers an efficient way to transport 400 gigabit Ethernet. And we do get a line side transport for DCI reaches, so 1 or 2 spans with 800G lambdas, while on the other hand, the lower rates get a boost in terms of transmission reach. So using 800G modems, it means we actually get 400G lambdas into metro and long haul. So while using today's 600G modems, it was not possible to transport 400 gig with a single wavelength into long haul. With future 800G modems, single lambda 400G will cover all the various use cases. So I'll turn over to Kent, who will go into more detail on this.
Okay, thank you. So here we're going to look at some analysis that's been performed to try to determine the benefits that you can get from using a higher baud solution in a typical network environment. So for this analysis, we're showing 2 different networks. One is a regional size network, which is the Germany network. It's got an average path length of about 300 kilometers, and there's a continental U.S. network that has an average path length of around 1,000 kilometers. These networks were both loaded with traffic, and wavelengths were routed around the network using different paths with a fixed channel spacing, and then they were filled until they reached the point where there was about 2% blocking. And this is just important to note because the same method was used to load the network for each generation of technology that we looked at. So at the bottom there on the graph, you can see the distribution of the path lengths that were achieved for the different services that were routed across the 2 networks. So ultimately, given these 2 networks, the question is, how does increasing the baud affect things like the overall capacity of the network and the number of modems required to satisfy the demand? Let me go ahead and advance it over to the next slide. So the results of the analysis are going to try to get an answer for that question from the title of the webinar about double the capacity and double the performance. So we showed some results for 3 different generations of coherent modems. The first being a 100 gig, 200 gig capable modem. The second is a 56 gigabaud solution that's capable of up to 400 gig per wavelength. And then the third is WaveLogic 5 Extreme running at 95 gigabaud with next-gen DSP enhancements. So here you can see at the top, the average modem capacity is more than double for the 56 gigabaud, and it's 3.4 times higher than the 100 gig, 200 gig modem. You can also see the newest generation running at the higher baud can achieve over 700 gig on average for the Germany network and over 600 gig per modem capacity on average for the US network. The next graph down is the total network capacity. So you can see the network capacity in total is going up, and this is because we're keeping the baud and the channel spacing constant for each generation solution, but we're just adjusting the capacity up and down for a given route based on the distance and the margin that's available. And so as we have better performance and a higher range of tunability on the line, we move from not just having 100 gig or 200 gig, but the ability to go all the way up to 800 gig on the line. You see the capacity increases. Of course, you see we don't get to a net doubling of network capacity here. Overall, it's just under 50% improved network capacity. Now, the number of modems required to satisfy the demand, which, as we mentioned before, the capacity is going up, but the number of modems required is decreasing significantly. So again, less than half from the previous generation and about 70% less modems required than the 100 gig, 200 gig option. So now you're getting more network capacity with fewer modems. And of course, the power consumption is decreasing as the baud goes up. So at the end of the day, the question is, what does this mean? With next-gen coherent technology, you get improved performance to push more bits farther. Now, it doesn't translate into a doubling of network-wide capacity based on a typical set of routes. However, you do get significantly more capacity per modem, and you get fewer modems overall and a lower power requirement, all of which translate into reduced costs for the equipment and reduced ongoing costs for the operation. And then just one other point I wanted to mention with respect to these two networks is that 400 gig Ethernet can be supported on almost all of the network paths using a 400 gig line rate at 95 gigabaud. So this technology is definitely an enabler for new high-speed differentiated services using 400 gig Ethernet. So with that, I'll go ahead and pass it back to Tim to take us into the next section.
Thanks, Kent. That was very informative and helps the answer if double the capacity equals twice the performance. In the next section, our sponsors will present their company's new technology and products, and Kent will lead us off with Ciena's WaveLogic Extreme. Okay, thanks. So at Ciena, we're seeing two types of network requirements, and you saw some of that actually in some of the other slides as well. We're seeing requirements for footprint optimized solutions as well as performance optimized solutions. Ciena has invested in both of those technology paths, so we're bringing to market small form factor pluggable solutions with reduced power and space, and that's with our WaveLogic 5 Nano. And then high-performance solutions up to 800 gig per wavelength with WaveLogic 5 Extreme. And this is really what we've been focused on for this webinar. Now, this technology is rolling out across our portfolio, so that means it's on the 6500, and we also just announced a new wave server platform that's optimized for WaveLogic 5 Extreme as well. Additionally, Ciena is evolving the photonic layer with different form factors for deploying a flexible open line system. More and more people are looking at solutions to be able to increase the overall capacity of the fiber plant. And the 6500 RLS has an integrated C and L band solution that's designed to meet network operator requirements where they're really demanding that you can double the capacity with the L band, but do it in an easy way to add in those new L band wavelengths without impacting the existing network or impacting the existing wavelengths. They don't want to have to do any re-engineering or tweaking of amplifiers in Raman, for example. So the combination of
this next generation coherent modem with capacity up to 800 gig and an open compact modular photonic line system is all available from Ciena, and we're ready for the 800 gig era. And so here we just wanted to give an example of this technology being used in a network. So this was an industry first single carrier 800 gig field deployment across a live production network with Southern Cross. It was to connect 2 data centers with 800 gig on the 6500 platform. So subsea operators like Southern Cross are able to double capacity, achieving up to 400 gig per wavelength depending on the type of cable. And Southern Cross can also take advantage of the programmability offered with WaveLogic 5 Extreme to use a single programmable modem to run at rates like 400 gig, 500 gig, 600, or 800 gig to maximize their capacity and performance in the network. So this is a real-world example of the technology in a live network. And now I'll go ahead and pass it over to Mohammed.
Max. Max, you want to go ahead? Sorry. Yeah, sorry. I think we have a sequencing problem. So yes, from Fujitsu perspective, I think Fujitsu has a history of offering innovation in coherent technology. With generations of DSP technology improvements, Fujitsu have offered series of systems like T300 using 20 nanometer DSP, using 100 and 200 gig rates. And then lately, T600 using NEL Terra DSP, that is 16 nanometer, and a variable bandwidth transponder. And we will also be bringing coherent pluggable optics in the next generation T700 muxponder and a transponder to market this year. And we also have plans to offer 96 gigabaud and higher baud rate for much higher data rates. We are working closely with our customers to understand their timings and their requirements. And I think beyond coherent, to further increase the capacity, like Max has mentioned, Fujitsu is actually working on some innovative ideas like translambda that fit seamlessly into existing networks and can transmit wavelength from any generation of C-band transponders, but using L-band or S-band of the spectrum. So basically, from operator's perspective, transmission is in the C-band, but under the hood, that is converted into other bands to take advantage of the extra capacity of the fiber. It is done through all optical wavelength conversion, and it's fully transparent to data rate, channel width, modulation, and so on. So basically, it's a future-proof capacity multiplier. And I think that is an innovation outside the transponder box. And we need more new tools like these to continue improvement in the fiber capacity. And now I will hand over to Max.
Thanks. So talking about Huawei's portfolio, we do have sampling our 800G mini MSA type module, which offers a 200G to 800G tunable capacity. We have demonstrated the 800G functionality of this device in a recent field trial with China Mobile, to see on the right side, the transmission over 80 kilometers connecting 2 data centers. This, at the same time, this device offers long haul and ultra long haul capabilities when dialing down to 400G or 200G line rates. In parallel, of course, we offer the compact market and have our CAP and CAP2 modules, which have 100G and 200G modes, which really long haul. So the 200G modes with PCS in that module is an almost direct replacement of classical 100G QPSK in terms of reach and flexibility in a 50 gigahertz spectrum. Our 800G module is available across all of our popular platforms, the OSN 9800 U32, and the smaller, more compact M24 switch, as well as the OSN 1800s for metro applications. And that field trial that I mentioned was done using the latest OptiTrans's DC908 platform for DCI applications from Huawei. Tim, bring it home.
Thanks, Maxim. We're running a little bit late, so I'm going to try to go through this quickly. But as I mentioned before, Omdia has been developing these models looking at deployed bandwidth, new deployed bandwidth by line rate. And this is showing the history back from 2016 with forecast up to 2023 with how we see this breaking up by line rate. Now, as most people know, there's been a broad move to kind of these multi-rate coherent modems, which makes things more complicated. But we're actually looking at the type of modems deployed, and then coming up with models of the line rates that are actually used to look at the overall deployed line rates. In 2020, we expect that 200G multi-rate will have the largest deployment, and many of these will be in the CFP2 form factor, but we expect that 200 gig will be the largest deployment and an important line rate going forward. By 2023, however, 400 gig plus, which includes the 600 gig and 800 gig, it's primarily that, will be responsible for over 50% of the newly deployed capacity. You know, this new 7-nanometer DSP technology and higher speed electronics and electro-optics are being deployed for high capacity DCI, metro, regional, and long hauls. Networks. Trials are starting in 2020, and we expect these will start deploying in commercial applications late 2020, early 2021. Specialized 400 gig access and aggregation starts to ramp in 2020. So what's this? This is really 400 ZR. We expect there will be sampling of that this year, and then the commercial deployments in 2021. I should say, however, that before I said 600 gig is in deployments now and going forward. We expect that deployed bandwidth new deployed bandwidth actually will reach approximately 250 petabits per second in 2023. So back to the question, 800G technology, does double the capacity mean twice the performance? It's a complex question, and it's really a yes and no answer. And, it depends on the parameters that you're actually looking at. From Kent's example, yes, it does. It reduces the number of coherent modems by at least a factor of 2 as compared to going with 100 gig, 200 gig technology, which is an important cost driver. And it increases the modem capacity 340% over 100 gig, 200 gig, and 50% over 400 gig. But in other areas, it doesn't increase the total network capacity, and although very impressive gains in power dissipation, it's not double or half that. So it's a kind of a yes and no, a complex answer, and it really depends on the parameters you're looking at. Probably the most important or more important question is, what can this new technology do in practical networks? The new 7-nanometer DSPs and higher baud rate coherent optics should help cost-effectively scale network bandwidth to keep pace with demand. It's an important new technology. I think all the panelists agree on that. It's good to see that new amplified spectrum can be used to increase capacity, reducing or delaying the need to light new fiber. This is an important parameter. And, one of the other things, the industry is really starting to move to application-specific DSPs and coherent modems with the goal of, focusing on an application and making it so it works for that and is the most cost-effective solution. So I thank our sponsors, Ciena, Fujitsu, and Huawei, and we'll be closing the webinar and moving over to the Q&A session. I'm going to turn it over to Alan for a quick concluding remarks, and then we'll start the Q&A session.
Thanks, Tim. And just a reminder to everybody to please submit your questions and comments in the Q&A widget there on the side of your screen. We do have a lot of questions coming in. And also, please remember to download some of the resources that you will find in the resource list, including the slides from today's session, as well as that special report that Tim Monk authored as well. So that is all there, as well as some of the information provided by our sponsors today. So with that, let's get into all these questions. Tim, let me throw it back to you.
Okay, thanks, Alan. I'm going to start out with a first question. What type of network operators or networks are interested in 800 gig modems? Is there a specific market segment where they will be deployed? I'll take this and then throw it over to anyone else that wants to answer. Really, you know, where I see this being deployed, at least initially, is really in high capacity nodes, long-haul networks, some metro networks, but really the high-capacity nodes between major cities, if you will. I don't know, Kent or Maxim or Mohammed, do you want to add further comment to that?
Sure. So yeah, I think you know, we're seeing that having a modem that's programmable across a range of line rates up to, and obviously including 800 gig, is something that's going to be important for several different types of network operators. So not just, you know, one specific case. We talked about in our presentation a little bit about the subsea market, for example, with Southern Cross, but service providers are also interested in this. We just had an announcement with Verizon a few days ago where they turned up 800 gig across their live network. MSO cable operators are interested. Comcast also had an announcement in the last few days around 600 gig field deployment between Newark and Pittsburgh. And really, we're seeing interest even in other areas like government, research, and education. We also had an announcement with Internet2, who did a 400 gig wavelength between Chicago and Denver. So it's definitely high capacity applications, high growth applications, but probably a variety of different type of network operators can benefit from this technology.
Thank you. Next question. This is a question for Mohammed. Can you please elaborate on the changes and upgrades that you stated are required in the line system for 800G transmission?
Sure. So I think we have some standard options that are either being used or offered from the vendor community. We have been using 50 gigahertz line system that transitioned over to 75 with the current generations of transponder, and as I said earlier, there's a lot of investment that has gone into it. And then next logical step would be 100 gig or 150 gig as we go along with the higher baud rate. And anything in between kind of cause that idea that, hey, we need to have something either customized or very flexible line system that can handle the channel widths of like 112.5 or even 125. And that also has a direct impact of how we manage the channel and how we do the channel planning. Because that, with those kind of options, it starts to become more complicated. And that's what I was alluding to, that although we have flexibility, we just need to have a lot more complicated options to handle that, stitch it, and harness that flexibility. We need some more options within the line system to handle these new baud rates that are coming out of a commonly used channel with options.
Thank you. I think we have time for hopefully one more question. And this question is, which Ethernet switch SoC supports 800G? Maxim, do you want to take a shot at that? Or?
Yes, thanks. So as said before, there is no Ethernet standard which defines 800G, and likely there will not be anyone in the next few years. However, 800G here is a line rate, and it's an efficient way to transport multiples of 400G, so the next big thing in the datacom market. as well as transporting 8 times 100G or 4 times 200G. So in a way, our switches, or everyone's switches, will support the multiplexing of all these lower rates. So 800G is in the end the high-end solution for up to 400 GE transport. And should in a few years from now IEEE define the actual 800 GE rate, then of course will be supported in the next generation of products.
Thank you, Maxim. I think that's about all the time we have for Q&A. We're past the top of the hour. Please, thank you for submitting your questions, and the panelists and I will be following up with these questions via email with you. Thanks everyone for participating in this webinar. I hope you found it informative and helpful, and have a good rest of your day.
Thank you, Tim. And just a few final comments. I want to thank also our panel for participating in our webinar today, and for Tim for leading our discussion as well. So an archived version of this webinar will be made available shortly. Feel free to come back and view the session again, or even share it with your colleagues. A short survey will pop up at the conclusion of this webinar, so please take a few moments to fill that out. And also continue to follow us on Twitter and LinkedIn for information on future webinars from Omdia, brought to you by Informatech. So again, thank you for joining us, and have a great rest of your day.